Infinite limits, limits at infinity. This is saying what happens to the output as the x value, as the input becomes larger and larger and larger. Is the output approaching a certain value? So in the case of 1 over x, we're thinking about what happens as we plug in numbers that are bigger and bigger and bigger in the denominator, right? 1 over 10, 1 over 100, 1 over a million, 1 over a billion, right? Those outputs are approaching 0, and it makes sense because we know what the graph of this looks like, right? It's approaching that horizontal asymptote at y equals 0. So we would have the same limit as x approaches negative infinity. So limits at infinity are really just asking, is there a horizontal asymptote, or is this function just becoming bigger and bigger and bigger? Is the output becoming bigger as the input becomes bigger? Or is there a horizontal asymptote? So let's look at a couple examples. Alright, in this example, we should notice right away that the degree in the numerator is smaller than the degree in the denominator. And this is why infinity is kind of crazy, because this is going to be very large, right? But at infinity, the bottom is so much larger that the top is basically nothing, right? So what ends up happening is x goes to infinity, the bottom becomes so big that the output is going to have to approach 0. So this is just going back to our horizontal asymptote rules. If the degree is bigger on bottom than on top, then we're going to approach an HA of 0. So this infinite limit is equal to 0. Next example, we have 2x to the 4th and over 5x to the 4th. So these are both degree 4. So remember in class we talked about if we plug in inputs to the numerator and plug in inputs to the denominator, we're going to get different outputs. But as x approaches infinity, those outputs are going to become closer and closer together, right? So it's because they have a matching degree, and the highest exponent is the only one that ends up really mattering for the output when x becomes really large. So what ends up happening is the x to the 4ths kind of cancel each other out, and then the other stuff doesn't matter because it's so small in comparison, and then all that's left over is the 2/5. So this is the case where we approach the fraction made by the leading coefficients of the denominator and the numerator. So we approach 2/5. So in this case, kind of flipping that first case, now the numerator is bigger than the denominator. We have a degree 3 over a degree 2. So the numerator is going to become so much bigger than the denominator that this output is going to become really, really large. It's not going to approach any particular limit. It's going to be unbounded and just approach infinity because we have big over small. So remember how we kind of shorthanded this is we said small over big, that goes to 0. We said if there's a tie, we go to the fraction caused by the leading coefficients. And if we have big over small, well, that's just big, right? That's just going to go to infinity. Okay, last example. These types of examples, this function really doesn't serve that much of a purpose other than they end up being good functions to make you critically think about the horizontal asymptote, because what it does is this allows us to have 2 horizontal asymptotes, which was a tough topic from last unit that we're going to revisit. So again, we're plugging in negative infinity here, so really big, really big negative numbers, right? So normally we wouldn't be able to just take a square root of this first term because there's these other terms, right? So we can't just square root this one. But at negative infinity, these other terms are going to be so insignificant that we can just cross them out, right? And then same thing down here. These are so insignificant that we can cross them out. Just like we talked about before earlier in the video. Sorry, it cut off there for a second. Okay, so because at infinity we can just treat it like it's just the first term, then we can take a square root of that first term, which is going to be 8x to the 7th power. And that's going to be over 3x to the 7th. So we would say that the HA is approaching 8/3. But the thing is, we're approaching negative infinity. And if you plug in a negative value to x to the 7th, you're going to get a negative result, right? A negative times 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 a negative is a negative. But if you plug in a negative to the 14th power, I'm not going to count out 14 negatives, but negative to an even power is going to come out positive. So we end up with a positive on top, right? A positive on top, and then we end up with a negative on bottom. And a positive divided by a negative is going to be negative. So when we approach negative infinity, we're actually going to approach negative 8/3. And if we said this is the limit as x approaches positive infinity, this would approach positive 8/3. Now, don't forget that if this were an even degree, so let's say this were 16 and this were 8, well then, yeah, the limit as x approaches negative infinity would still be positive 8/3 because we'd end up with a positive over a positive. We only end up with this potential negative HA if this is an odd degree on bottom, and then when we square root, they end up having a matching degree. Okay, so we'll keep working on these types of problems. These ones are a little bit tougher than the other 3 earlier in the video. Okay, so you should be able to do the next few Desmos problems on the activity now.